On the previous chapter, we did an overview of how satellite communications work and the importance of an LNB in the receive chain. We are going to cover the following issues. What is 5G? What is the 5G spectrum? What frequency bands will it use? 5G base station versus SATCOM antennas? How 5G signals end up in SATCOM systems? 5G interference, what does it look like? 5G interference mitigation solutions, bandpass filter, BPF, and external BPF, EBPF.
5G interference mitigation. Chapter 4. The majority of commercial 5G networks are relying on spectrum in range of 3.3 and 4.2 GHz. This momentum makes it vital that regulators assign as much continuous 5G spectrum as possible in the range. In long term, the more spectrum will be needed to maintain 5G quality of service and meet growing demand. This includes more spectrum in the 3.5, 4.8, 6, and 10 GHz ranges, which will all be considered at WRC 23. As you can see in the picture, due to the interference from 5G signals into the downlink of SATCOM C-band services, we need to apply a bandpass filter in order to mitigate this interference. 5G C-band bandpass filter will have a low insertion loss and steeper skirts that roll off quickly and high stop band rejection. Furthermore, it will be easily installed between the feed horn and the LNB, and it's suitable to use with the C-band LNBs. It is environmentally sealed and it is moisture resistant. An LNB rejects the truss-reel interference. An LNB rejects the reel interference in C-band, which can be from 5G rather than another C-band transmitter. Moreover, it mitigates interference signals less than -25 dBm without degradation. Even more, it can be used with a C-band bandpass filter for additional 5G rejection. 5G signals are picked up in satellite systems through the SATCOM antenna, and the relative position and pointing angle of the 5G antenna and the SATCOM antenna will determine how much interference is received. There are 5 parameters which have a direct impact on the 5G interference strength. First, the SATCOM terminal elevation angle to the satellite, which is shown by theta. This is the elevation towards the satellite. The second parameter is the elevation angle between the terminal and the 5G antenna. The third, estimate angle between terminal to the satellite and 5G antenna. The fourth, the distance between 5G antenna and the terminal, as shown in the picture marked by the letter D. The fifth is the EIRP of the 5G base station. These 5 parameters will determine the value of the interference and can make the mitigation process easy or difficult. The antenna patterns of both 5G and SATCOM antennas play a role as well. SATCOM antennas are highly directional, providing some mitigation because they have low gain outside of the direction of the antenna. 5G antennas are usually more uniform as they are meant to cover a certain area. 5G signals are high power up to 75 decibel milliwatts. SATCOM received signals are low power between -100 and -80 decibel milliwatts. Thus, even the low off-axis gain of the SATCOM antennas does not usually provide enough mitigation. There are 4 main factors that 5G interference impact the LNB performance. High power signal at the LNB input can cause gain compression or saturation, noise floor degradation on wanted intermodulation products, and that high power signals at the output of the LNB can degrade the model's performance. In the picture, you can see the output of a typical LNB with an interference signal at 3.6 GHz. Marker 2 is showing that the interference signal with the power of -24 decibel milliwatts. The desired signal is at 3.95 GHz at -88 decibel milliwatts, shown on marker 1. All the other spirits is intermodulation products between the interference signal and the desired signal at the LNB LO. This is a simple simulation with 2 CW signals. Real 5G interference will be less clean. Intermodulation seems to be the first symptom. LNBs are essentially wideband amplifiers designed to add very little noise. Since they have no filtering, they have no way to suppress unwanted in-band signals like 5G. There are 4 methods that help mitigating 5G interference. With external filters, you can suppress the interference signal, but introduces losses, especially on filters with small guard bands. And they also add more insertion loss, impacting the system G over T. LNBs with integrated BPFs has less impact on the G over T, but does degrade the noise figure. Its filters are not as narrow and need wider guard bands. These LNBs are also designed to have a high-power mixer to minimize intermodulation products. LNBs with switchable BPF acts as an LNB with an integrated BPF that can switch filters in and out. They're useful in situations where the interference is intermittent, limiting the spectrum, and in other times can use full spectrum. Hybrid solutions, which uses both external filters and integrated filters, offer the best mitigation, but increases loss and degrades noise figure, making their impact on G over T significant than just external filters or LNBs with filter. They're used in extreme circumstances where the interference has high power and close to the frequency that is used in the satellite signal. On this plot are shown the external BPF, which reduces the power of the 5G interference while passing the desired signal. The effectiveness of the filter and mitigation depends on how close the 5G interference is to the passband. The two filter responses are for a standard BPF and an extreme bandpass filter. The extreme bandpass filter is needed when the guard band between the 5G signals and the desired satellite signals is small, for example, 20 MHz. The drawback is higher insertion loss. The left plot shows an LNB with two integrated bandpass filters in the front end of the LNB. This topology reduces the impact on noise figure reduction by having one amplifier stage at the input. The bandpass filters also reduce the impact of signals saturating later stages of the LNB. Typically, the mixer has also high power than normal to reduce intermodulation. The IF filters are tuned to suppress the interference signals. Two snapshots from spectrum shows the effect of BPF filter mitigating the interference. The left plot is an LNB with an integrated BPF, and the right one is a normal LNB. Marker 5 is the interference which has been mitigated significantly for almost 22 decibels. If we compare the solutions described, we can see the performance of the three cases, including external bandpass filter, integrated bandpass filter, and a hybrid solution which combines an external BPF and an integrated bandpass filter. The red signal is for an external BPF, and as you can see, it has lower rejection and higher roll-off factor. The green signal is for the integrated 5G filter, which has a better performance than the BPF, but poorer function compared to hybrid solution. Finally, the blue signal is for the hybrid solution, which uses two bandpass filters.